Welcome to Infinite Mind Channel, the place where curiosity meets knowledge. Today, we're diving, quite literally, into a topic that might have sparked your interest. What would happen if we transferred high voltage to the ocean? It's an intriguing thought, isn't it? To explore this, we first need to understand the basics of two key elements: electricity and conductivity. Electricity, as we know, is a form of energy resulting from charged particles. And conductivity? Well, it's the measure of a material's ability to allow the flow of electric charge. The ocean, being a vast body of water with dissolved salts, is a good conductor of electricity. But what happens when this conductor comes in contact with high voltage? Does it create a spectacle of sparks, or does it have a more subtle effect? Have you ever wondered about these things? Today, we're going to find out. Before we dive deep into our main topic, understanding some fundamentals about electricity is crucial. So, what exactly is electricity? In the simplest terms, it's the flow of electric charge. This charge is usually carried by electrons in a wire or other conductor. Now, this electric charge doesn't just move on its own, it needs a push, and that's where voltage comes in. Picture voltage as a kind of electric pressure. It's the force that pushes electric charge along. The higher the voltage, the more force there is pushing the charge and the more electricity can flow. But hold on, if voltage is the force, then what is current? Good question. Current is the actual flow of the electric charge, or how much charge is moving past a point in a given time. It's kind of like the speed of the electricity. More voltage means more current, assuming the resistance stays the same. Ah yes, resistance. That's another key term. Resistance is anything that slows down the flow of electric charge. Imagine you're trying to push a sled through the snow. The snow provides resistance, making it harder for you to push the sled. In an electrical circuit, things like the thickness and length of the wire and the material it's made from can all create resistance. Electricity is generated in a variety of ways, from burning coal or natural gas to harnessing the power of the wind, sun, or even nuclear reactions. Once generated, the electricity travels through a network of wires and transformers, which step up the voltage for long-distance travel, then step it back down again for safe use in our homes and businesses. So, to sum up, electricity is a flow of electric charge pushed along by voltage, with the actual flow rate called the current, and any obstacles to that flow called resistance. Now that we've got the basics down, we can delve into the heart of our discussion. The ocean isn't just a vast body of water, it's a highly conductive one at that. A conductor, in the simplest terms, is something that allows electricity to flow through it easily. But what makes the ocean such a good conductor? The answer lies in the salt. You see, seawater isn't just water. It's a cocktail of various salts and minerals, the most abundant of which is sodium chloride, better known as table salt. When these salts dissolve in water, they split into charged particles called ions. These ions are the key players in the conductivity game. They're like tiny little delivery trucks carrying electrical charge from one place to another. When an electric current is introduced into salt water, it doesn't just stay in one place. The ions in the water pick up the charge and start moving, creating a flow of electricity. This is why salt water is such a good conductor. It's full of these charged particles, ready and waiting to carry an electric charge. But what about the sheer size and depth of the ocean? Does that affect conductivity? Absolutely. The larger and deeper the body of water, the more ions it contains, and therefore, the better it conducts electricity. The ocean, being the largest and deepest body of water on Earth, is a veritable superhighway for electric current. You might be wondering about the temperature and pressure of the ocean. Do they impact conductivity? Indeed, they do. Higher temperatures and pressures increase the mobility of ions, which in turn enhances conductivity. And since the ocean's temperature and pressure vary with depth, so does its conductivity. But what about the purity of seawater? Surely that must have an effect. Indeed, it does. The purer the water, the fewer ions it contains and the less conductive it is. But let's be clear, even the purest ocean water contains enough ions to be a good conductor of electricity. So we have a highly conductive ocean and high voltage electricity. What happens when they meet? Imagine this scenario: a high voltage line falls into the ocean. What happens next? It's a question that may sound straight out of a science fiction novel, but the answer is grounded in the laws of physics, and it's quite fascinating. You see, when high voltage meets the ocean, a flurry of immediate effects take place. The first thing to understand is that the electricity doesn't stay in one place. It begins to disperse, spreading out in all directions from the point of contact. This happens because water, particularly salt water, is a good conductor of electricity. The sodium and chloride ions present in seawater facilitate the flow of electric current, causing it to spread out almost instantly. But as this electricity disperses, it doesn't just vanish into thin air, or rather thin water. It transfers its energy to the water around it, causing a rapid increase in temperature. This sudden heating can cause the water to boil and create steam if the voltage is high enough. A spectacle of bubbles and steam, quite dramatic yet potentially dangerous. Speaking of danger, the marine life in the vicinity of this high voltage entry point would certainly be at risk. The electrical discharge can be lethal to fish and other sea creatures, causing immediate harm. Not to mention, the sudden heat spike could also prove harmful, disrupting the delicate balance of their environment. But electricity in the ocean isn't just about the immediate spectacle of boiling water and fleeing fish. It's also about the subtle, unseen changes happening beneath the surface. These changes might not be as dramatic, but they are equally, if not more, significant. The introduction of high voltage into the ocean can lead to chemical reactions within the water. It can cause changes in water composition and pH levels, which can further impact the marine life, potentially causing longer-term ecological disruption. But that's not all. There are also long-term effects to consider. Because while the immediate effects of high voltage entering the ocean might be visually startling and scientifically intriguing, it's the long-term impact that really begs our attention and concern. The immediate effects are devastating, but the long-term effects could be even more so. Let's delve deeper into the potential long-term effects of high voltage in the ocean. To begin with, one significant consequence is the alteration in water temperature. When high-voltage electricity is introduced to seawater, it can cause a rapid increase in temperature. This rise in temperature not only impacts the immediate area around the electrical source, but can also influence the overall oceanic temperature over time. This may seem trivial, but even a slight change in water temperature can have a monumental impact on marine life. Many species of marine animals and plants have adapted to thrive in very specific temperature ranges. A sudden or sustained temperature shift could lead to the death of these organisms or force them to migrate, disrupting the balance of the ecosystem. Speaking of ecosystems, direct damage to marine life is another long-term effect. High-voltage electricity can cause serious harm to marine creatures, from the smallest plankton to the largest whales. This damage could lead to a decline in biodiversity, which in turn affects the entire food chain. Over time, this could result in the collapse of entire marine ecosystems, a catastrophe that would have ripple effects felt far beyond the ocean itself. Lastly, let's not forget the potential effects on climate. The ocean plays a crucial role in regulating the Earth's climate. It absorbs and distributes heat around the globe, influencing weather patterns and climate zones. If the temperature of the ocean were to change significantly due to the introduction of high voltage, it could potentially disrupt these patterns. leading to unpredictable and potentially severe weather events. In conclusion, the long-term effects of introducing high voltage to the ocean are manifold and potentially catastrophic. From disrupting marine ecosystems to altering global climate patterns, the consequences are far-reaching and could have a profound impact on our planet. So, transferring high voltage to the ocean would have far-reaching and potentially catastrophic effects. The ocean and high-voltage electricity are a dangerous combination. We've journeyed through the basics of electricity, explored the conductivity of our oceans, and witnessed the meeting of high voltage and the vast sea. Through this, we've come to see the potential harm that can occur when these two powerful forces collide. High voltage electricity in our oceans can have devastating effects on marine life and can also pose serious risks to human safety. It's crucial to remember that electricity isn't a plaything. It's a powerful force that demands respect and careful handling. Protection of our oceans is also paramount. These vast bodies of water are home to an incredible array of life and play a critical role in our planet's health. We must tread carefully, making informed decisions that prioritize safety and sustainability. Remember, knowledge is power, and with power comes responsibility. Let's use our knowledge to make informed decisions and protect our oceans. Thanks for joining us on Infinite Mind Channel.